In this lecture, we want to start using the formulation we introduced and proved for the ratio of the angular velocities of two rigid bodies between which the motion is transmitted. We start from examples of direct motion transmission in this lecture, and in the next lecture we will continue with examples of indirect motion transmission. Let's firstly make a review of our formulation. It says when motion is transmitted between two rigid bodies, we can define and draw a line of transmission as well as a line of centers between the two bodies we considered as the driver and the follower. If we call the intersection of the line of transmission and the line of centers as point Q, then using this key point, we could say the ratio of the angular velocity of the follower, omega 2, to the angular velocity of the driver, omega 3, is equal to the ratio of O3Q to O2Q. O2 and O3 are the rotation centers of the driver and the follower links. Later in one of the upcoming sections, we will see that point Q is in fact the center of rotation that we can imagine between the driver and the follower links. Meaning that we can think the driver and the follower are kind of pinned together at point Q. In other words, point Q is the center of rotation of the follower with respect to the driver. If this center, point Q, is a constant point, then the ratio of the angular velocities remains constant. Otherwise, we have a variable ratio of angular velocities over time. We will later see that this point Q is called an instantaneous center because it constantly changes during the motion of the system and might be valid only for an instant, meaning that in the next instant it might be somewhere else. If we rewrite the relation in another form, like saying omega 2 times O2Q is equal to omega 3 times O3Q. In fact, both of these expressions describe the velocity of point Q. In this expression, we assume that point Q belongs to link 2, and in this expression, we assume that point Q belongs to link 3. The reason why we can say this is because point Q is the instantaneous center between the links 2 and 3. Anyway, if it is complicated to you, no worries. Just forget about it. We will soon have a full section dealing with instantaneous centers. But for now, we just need to use this ratio to see how the angular velocity is transmitted from the driver link to the follower link. Let's have our first example where, as you see, there is a sliding contact between the links. We name them 1, the ground as usual, 2 for the disc, which is the driver and rotates clockwise, 3 for this rigid link, which is the follower and receives the motion from the disc via the sliding contact between them. First of all, we need to find point Q. The line of transmission passes through this contact point and is along the normal direction of the surfaces in contact. For the line of centers, O2 is the center of link 2 and O3 is the center of link 3. The line of centers is the line connecting them. This intersection is point Q. Now we can say the ratio of the angular velocity of the follower, omega 3 to the angular velocity of the driver, omega 2, is equal to the ratio of O2q to O3q. We should also notice that since point Q is in between the two centers, the two angular velocities are at the opposite direction, meaning that if the driver rotates clockwise, the follower must rotate counterclockwise. It is important to also determine the relation between the directions of the angular velocities. In the next example, we have two disks in rolling contact. One is the ground. Let's assume this smaller disk is the driver and rotates counterclockwise. Number 2, and its center O2. And this bigger disk is number 3, which is the follower, and its center is O3. The line of centers is clear. The line connecting O2 and O3. The line of transmission in this case is a bit confusing. Usually in a direct contact, the line of transmission is along the normal direction. But in this case, no motion is transmitted along the normal direction because the driver is not pushing the follower along the common normal. Instead, the rolling motion is transmitted from disk 2 to disk 3 along the tangential direction. So the line of transmission is along the tangential direction in case of a rolling contact like this. If I draw the transmission line, then the intersection is at the contact point. As usual, we name it Q. Now we can say the ratio of omega 3 to omega 2 is O2q over O3q. We should also notice that since point Q is in between the two centers, the angular velocities are at the opposite direction. Therefore, the follower disk must rotate clockwise. In the next example, we have a case of direct motion transmission via a pin on a slot joint. Let's name the links. 1, the ground, 2, and 3. Link 2 is the driver and rotates counterclockwise. We have already learned that when there is a pin on a slot joint, the line of transmission passes through the pin and is perpendicular to the slot. Something like this. For the line of centers, the rotation centers are O2 and O3. If I connect them, O3 to O2, and extend until it intersects the line of transmission. If I call it as Q, then I can say omega 3 over omega 2 is O2q over O3q. And since point Q is somewhere outside of the distance between the centers, the angular velocities must be at the same direction, meaning that link 3 must also rotate counterclockwise. In the last example, there is a sliding contact here between links 2 and 3. And there is a rolling contact here between link 3 and the ground. Number 1 is reserved for the ground wherever it is, here and here. If we assume link 2 is the driver and rotates counterclockwise, we need the magnitude and the direction of the angular velocity of link 3, which we consider as the follower. For the line of transmission between links 2 and 3, which is the easy part. It passes through the contact point and is along the common normal of the two surfaces. For the line of centers, link 2 has a clear center, which is here, O2, but we don't see a clear center for link number 3. There is something new to learn in this example. Later, in the section of instantaneous centers, we will study in details about a rolling contact between a rigid body and the ground. But for now, we just need to know that in case of a rolling contact on ground, we can consider the rolling contact point as the center of rotation, meaning that this point, which we call O3, is the rotation center of link number 3 at this instant or at this moment. Therefore, for the line of centers, we just need to connect the centers O2 and O3. Then the intersection of this line with the line of transmission is point Q, and we can say omega 3 over omega 2 is O2Q over O3Q. And since point Q is in between the centers, the angular velocities are at the opposite direction. So link 3 must rotate clockwise. We should also notice that using this ratio, we can determine the angular velocity of the follower, omega 3, as a function of the angular velocity of the driver, omega 2. The ratio comes here, O2Q over O3Q. Notice that this relation usually also includes a sign to clarify if the rotations of the driver and the follower are at the same or opposite directions.